for the operation, and that means selling the product, ELI, to an international consortium that will sponsor and operate its life as a user facility after 2017. And for that, this ELI Delivery Consortium International Association has been founded, and you see here the status, the membership status. We have regular members, we have members which are have applied and are under considerations, and others who are seriously thinking, and we are negotiating about applications, and I'm seriously expecting France to join very soon, but the negotiations with France, as frequently, are not as easy, but there is a strong commitment. Yes, we will join, but let's talk about the conditions first, and that's okay. Then we have Portugal is now also trying to join, and Spain, Poland, and these are other countries, and Russia with the project which I have just presented is also a candidate. So, as a summary, a vision is becoming reality, and we are very grateful to Gerard for that, and hopefully from 2018, ELI, although not yet being an exawatt facility, it will still be the world's first international laser user facility, providing unique research opportunities like the CERN of laser research. If you want to learn more about the project, this is the relevant page. And all that remains to me on behalf of the whole ELI community is give my sincere thanks and expression of gratitude to Gerard for this wonderful initiative, and from all our friends from ELI, our best wishes for your 70th birthday.
So if 200 million tons of concrete seems weighty, I think we need to move to the next talk with Sir David Payne, who is going to put us on a high fiber diet.
Right, well, it's a great honor to be here to talk at the occasion of my friend Gerard's 70th birthday. So I'm going to tell you something about his latest ideas, because I've been Mouroo'd at a meeting which I'll tell you a little bit about. I have a picture at the end of the talk, where I got seduced by Gerard's visionary ideas into joining into the ICANN project, and I'm going to tell you a little bit about that, although I'm leaving others to tell you the full story. My job is to talk about fibers, because we haven't talked about those yet. And I think you're going to enjoy some of the things and some of the movies that I've got. Here is one. Great fun to introduce your talk with a laser marking machine. This is a fiber laser. And the fiber lasers are currently selling in the world market at something like several hundred a week. So it's a pretty big market, and the reasons for that are they're in all solid state, they are diode pumped, they're totally reliable, and they don't look like any laser that you've ever seen before. So I'm going to tell you a little bit about how that came about. And the first thing I would note is that I'm actually a refugee from the telecoms community, which is where I've spent most of my life. And managed to escape and I now pretend to be a physicist. And so this is how I got involved in these lasers, high-power lasers, and so on, which was finding something else to do with fibers after the telecoms market crashed in 2000. And so we were very successful in actually doing that. And first thing, though, I would like to do is to dedicate my talk, and it will become apparent, I think, in a while why I've chosen these three individuals. Charles Towns, of course, and here Charles Cowell, my very old friend that I've worked with ever since I was a tiny student, and of course Gerard, where we first met, I believe it was in 1990, somewhere around there, here in Michigan, actually. So, what is a fiber laser? Is the first question. And you all know this. This is a standard type of laser, such as, for example, a neodymium YAG or a glass, as we heard earlier. Pump modules, which might be flash lamps, or in this case, most lasers these days use diode pumps. And this is another thing which I would encourage people to look at what's happening in the semiconductor laser area, because this is an enormously growing field, and the prices are coming way, way down to figures of a few dollars per watt, fully packaged and fiberized. And of course, the problem, as we all know, is that this has got surfaces here, and the big thing you have to worry about is, of course, heat. And the heat distorts the resonator, and in some cases, as we heard from Todd, you can only fire this thing a few times an hour, because you have to wait for it to cool down, right? So what about a fiber laser? Well, totally different, of course. This has built-in integral reflectors, which are Bragg gratings. In fact, the pump is not done, it's just schematic like that. It's an all-fiber configuration, even for injecting the pump, which is why when you see what they look like a little later, they don't look like a laser. They look like a piece of electronic equipment. And of course, this gives you huge advantages because they withstand the heat because of their huge surface area. So if you remember Todd's talk, which was showing you these huge great disks, what we're saying, and what he is also saying, by the way, of course, was that if you take these great disks and you pour water between them and make them into rods, then you gain in heat extraction. Well, we're saying even more, pull them all out into fibers. And the volume, of course, still has to be the same if you want to keep the same amount of energy per pulse. But think of that. You take the disk, pull them into long fibers, filament them, and of course you don't get filamentation because they are a filament. So the large surface area then becomes a huge advantage. The core is close to the heat sink. This is something which most people don't really think about, which is that the mode is guided. And therefore, as you get thermal distortion, the mode just conforms and still remains a perfect Gaussian, or very close to perfect Gaussian. So they automatically adjust to their own resonator. And of course, silica has amazing heat resistance. It's the highest and most refractory of all glasses. So this is what one looks like. As I said, just looks like a piece of electronic equipment with the beam delivery optics coming out here. And in reality, the word fiber laser is a bit of a misnomer because actually, in most configurations, you use amplifiers with a seed laser up here. And I call this the internet in a box sometimes, because it's like a set of amplifiers, except as in the internet, what you do is you just maintain the signal constant. Here you let it build up through multiple amplifiers. And the world record remains at 14 kilowatts from one single fiber. And of course you can put multiple fibers together, so you can buy a 30, 40 kilowatt device if you want. So that's a little start to my talk, which is a seminar, everything you need to know about fiber lasers. But this is an important point, I think, that has been recognized by Gerard. And apologies to Heineken, but The fiber laser reaches parts that other lasers cannot reach. So for example, nobody uses neodymium in a fiber laser. It's so 70s, you know. Ytterbium is what you use, or holmium, or thulium. You just change it for whatever you want. As far as the neodymium is concerned, the only reason that it's used, in our view, is because it's a four-level system, but who cares if it's in a fiber? The threshold doesn't matter. So nobody uses it, right? A couple of experiments, but that's it. High average power with 50% wall plug efficiency. And that's huge. Typically, the fiber lasers are very close to 100% quantum efficiency. That leads you to another idea, which I'm going to tell you about in just a moment. And the frontiers are new wavelengths, the infrared. I don't have time to review all of this for you, but we're out to about between 3 and 4 microns now. We can also transmit that stuff all in silica, so that's a very exciting area. Short pulse, femtosecond and picosecond. I'm going to show you that in a moment. And massive parallelism, because for the first time we have a laser gain medium that costs almost nothing. So who cares how much you use? You can pull this stuff in commercially today. They pull 10 fiber lasers a second on one fiber drawing machine. So it opens opportunities which you may not have thought about, and I'm going to try and convince you that some of these things are really real. So here's my conversation with Gerard. He comes to me and he says, how about we do the next accelerator for CERN? So I'd had a few drinks, and so I said, yeah, why not? And he says, it's this stuff. And he was with Toshi at the time in Paris. And he said, well, there's this thing called laser wake field. And I'm going, is there? And he said, yeah. Well, what we do is we create this huge plasma plume, and we surf particles down that. And I'm going, yeah, okay. And he says, and we can use it for nuclear fuel transmutation if we can make a really cheap accelerator. We can make tabletop synchrotrons, ion beam therapy, and the latest idea, which is we can actually get rid of space junk by having a flying, huge fiber laser system, which is all at the femtosecond, and then we'll ping off each of the little tiny 50 Mach zooming around particles that are up there, which are left over from exploded satellites and things. So I'm saying, gee, this sounds pretty good, Gerard. And you know something, he's really convincing. And I've heard him talk recently on this one, and actually it makes one hell of a lot of sense. It really does. So I got completely taken in, oh, sorry, that's not the word. But a believer in this stuff. So this was what Gerard reckoned. There's really only one way to get high average power and high pulse power. As he pointed out, you know, NIF does, I think, it's 100 watts or something like that, average power. Not great. What we need is megawatts. So he says, how about we do a megawatt with a 10 petawatt peak power at 100 nanosecond pulse width with 50% efficiency? So I'm saying, yeah, okay, no problem. How much money have you got? which is a catchphrase which I learned when we first did the fiber laser, which I'm going to show you about in just a moment. So being just as ambitious as Gerard, I said, yeah, let's do that. But then I pointed out a couple of things. I said, well, you know, the trouble with fiber lasers, they're really good at high average powers, but they're pants at peak power. And he said, yeah, well, that's the challenge. So this is a typical commercial fiber laser working at about a kilowatt. Actually, they're usually nanosecond pulses. But the problem is, and it won't surprise you, is that a fiber laser is typically a few meters long, up to 10 meters long. It's got a core size of about 20 microns. And therefore, you start putting more than a peak power of around, working figure is 30 to 100 kilowatts, then you get every nonlinear effect under the sun. And the one that hits you first is usually Raman. Okay, so you've got to figure out ways of getting over that, and this is miles away from what we need to do for Gerard's vision. So we got to thinking about this. We said, okay, we recognize that the real forte of fiber lasers is average power, not peak power. So what we're going to do about that is we're going to do a couple of ideas came up, which is we'll distribute the power over multiple cores or fibers, such as this. We'll use very large cores and keep them straight. Now, this is interesting because you see what it's happening here. It's driving you back to conventional lasers. And you begin to ask, is there a sweet spot between a skinny little fiber and a big fat rod? Because that's the place that we're exploring, and in particular, this has been led by a group in Jena who's developed this idea, which is to keep a dead straight, large core. This is Jens Limpert's work. And you know, it's not trivial because you lose a lot of the advantages of fiber laser if you go this way, not least of which is the packaging capability. These things tend to be more than a meter long. But it's got world records for fiber lasers in peak power. So you can get up to about 1 gigawatt or so. So, or of course, use chirp pulse amplification, wouldn't you? Why else do you think I'm here? So maybe even use pulse stacking, because the rep rates that you need here that we're shooting for is maybe 10 kilohertz, something like that. So there's lots of room to stack, because fiber lasers typically run when mode locked at 100 megahertz, something like that. So there's another way that we've started to think, and this is very attractive and really is beginning to go gangbusters here, is to think about this, which is lasers pumping lasers. That was pointed out also earlier by Todd, but you know there's one big advantage you get using fiber lasers. I pointed out that they're about 100% quantum efficient. Therefore, it doesn't matter how many steps you take to get from your pump to your final laser wavelength. All you do is you distribute the quantum defect down the chain, but there's no other loss, which is counterintuitive, because you immediately think, well, I'm going to take a hit of 80% efficiency in this one, and then 40% in this one. And it's not like that. It's just one jump, and you can distribute it any way you like. So this becomes really about thermal engineering. What this does is it puts these are fiber lasers, pumping a final stage, which is very short, fat fiber laser. And the advantage is we've worked out that you can get about between 1 and 3% quantum defect. So in other words, for a kilowatt, you've only got a few tens of watts dissipation in the final stage. That's hugely important, because now what you're going to do is you're going to run your signal here. Coming through this is going to be, of course, chirp pulsed amplified, and you've separated out all the hard, heavy lifting stuff, all the nasty thermal stuff, into all these other lasers, which are standard fiber lasers. And so we've already got those, by the way. You don't have to develop those. What's happened here? Whoops. Okay. So, next part of the conversation. We could use beam combination. Right. How many fibers would we need to get to what Gerard is talking about? 100,000 phased together? Actually, this is not so silly. I pointed out it costs nothing, and each fiber laser then becomes relatively easy to make, and when you phase them together at the end, the more fibers that you have, the better will be the reconstructed beam, which needs to be close to diffraction limited, of course. So I said to Gerard, you know, Gerard, this is not a new idea. The burning mirrors of Archimedes from the siege of Syracuse. You remember this from your classical education? So I did a bit of searching around, and guess what I found? a film by Giovanni Pastrone made in 1914. Is there nothing new? So here he is. Here's the mirrors. Beam combination, right? So, this is wonderful. So here he is in the actual siege. As you will see in a moment, this you ought to take down, Gerard. Use this in your next proposal. So here it is being unveiled. As you can just see up here, all the mirrors. There we go again. I just love this next picture because it's so obviously in a bathtub. So, actually, we picked this idea up anyway for the DARPA project in 2002, which is where all this stuff came from L N Durvasula, who famously called me up and said, Dave, how much power could we get out of a fiber? And I famously replied, it's only a matter of money. And he said, how much? And I said, how much power do you want? And he said, meh, tell me, could you do a kilowatt? And I said, yep, that'll cost you 5 million. He said, done. So those days have gone, right? So this was what we put in. This is actually a slide from 2000, which said this is what we want to do. We were going to have these amplifiers like this. They would all be phased together. They'd need a phase control, of course. And the beauty of it would be we would have built-in adaptive optics, because you can vary and you can steer this stuff, right? So the problem was it had to be single mode, single frequency, single polarization. And we worked on this, and at the end of the project, we did 1.4 kilowatts of Brillouin-free single frequency, single polarization, at which point they took the money away. They said, no way are you doing that in the UK. And of course, this is the basis then for an extensive programs over here in the US. Okay, so there is one big difference though. This is CW. And I keep pointing out to you, you know, that this is what fiber lasers love. We love to have CW going through these things, or at least nanosecond. To do this for femtosecond is unbelievably difficult, because now you have to match the lengths. Because you need to, well, put it the easy way is you've got to have the pulses from each path overlapping in space when they get to the end, which is pretty challenging. So I'm going to show you the numbers in a moment. So here we go. This is how you do, of course, laser coherent beam combination with all these fibers together like this. This is showing for 64. And of course, we need coherent addition, and we require the fiber length matching 2 microns in length. So I wanted to show you the vision, which we put together here.
Ignition will commence in 30 seconds.
This is Gerard's
Icon laser ignition will commence in 20 seconds.
You notice we're going to call this the giant exasecond shimmering radiation.
Icon laser ignition will commence in 10 seconds.
And so I can search for what lies beyond the Higgs boson begins. the most powerful laser ever conceived, is switched on. This scenario belongs in the future, yet the research required to try and make it happen has already started. But exactly what is, I can't.
Existing huge laser experiments fire sometimes only 4 times a day. We're now talking about the possibility that you could do this with an average power so that it's on all the time.
The reason this is possible is because of a unique way the laser is conceived.
What happens is you start with a single seed laser, and then you split that into 8 different channels, amplify, split those channels into 8, and then split those channels into 8 until you get up to, say, 512 amplifiers. And then those 512 amplifiers, the beams have to be synchronized and brought together to make a single beam.
ICANN is an international consortium, initiated and coordinated by the École Polytechnique in France. The other principal partners are the Optoelectronics Research Center in the United Kingdom, the Fraunhofer Institute in Germany, and CERN in Switzerland.
So that's Gerard's vision. He takes all the credit for that. Unfortunately, this is a 14-minute video, so I only could show the front end before we got to Gerard's amazing part, but I'm sure he'll forgive me for that. My editing skills are just not good enough. So, to get back to the technology, and I really need to wrap up, so I'm going to go through this very, very rapidly. When you do all these things and you think about this, you come up with the following conclusions, which is that you need a packageable ytterbium large core fiber capable of about 20 millijoules output, all of which is very difficult for a fiber laser. You CW fiber pump it with another fiber laser. So this is beautiful because it takes the heat out of the signal path, and you put your signal pulses here. So notice that we're doing what's called in-band pumping. So we reduce the thermal load, and we get the fiber length way down so we can get more, a much lower, higher, nonlinear threshold. So this is another piece of parallel technology which I don't have time to go into, but this is these wonderful tiny hollow core fibers for beam aggregation. And so we think these are going to look a bit like this. And this is a real simulation of all the fibers to bring all these together. And these fibers are now down at losses of a couple of dBs per kilometer. So easily enough. And there's a recent demonstration from these guys here. The board, 80 gigawatts, 50 femtosecond pulses going through these fibers. So we think that part is just going to be fine. So I'm going to run through this to show you that we really have thought this thing through. This is what it's going to look like, and this is just one section. So you'll notice that there's 64, count them, fibers down here, and there's going to be anything up to 100 of these. Stretchers, the usual pulse stretching for CPA. You then select out of the packet. And then you run through amplifiers, succession of amplifiers. Then you have to bring them back together here through hollow core fibers. Stack and compress to give you your output, which in this case, for this one stage, you see that we've targeted 10 kilowatts, 10 kilohertz with a pulse energy of about a joule. So very challenging stuff. So let me finish. Oops, what I... but what Gerard has pointed out here is that massive parallelism is something that is now available to us, which you would not think about in other lasers. And that is revolutionary. And it's that kind of thinking which takes us to the next generation, I think. So thank you, Gerard, for pointing that out. I love working with you. You're always so stimulating. and happy birthday.
Melissinos going to tell us about the breakdown of the vacuum.
Well, thank you, Herb. Let's see if we can get the show on the road. I think we are here. And I think this one. All right. Well, this is a return now to old times rather than looking in the future. I first met, how did I meet Gerard? I think it was in the early 80s. We wanted to build an accelerator which needed a switching pulse. So I went to the laser lab, which I knew a little bit of, and immediately Gerard volunteered to give us a lab to do something with Bill Donaldson, who was in his group and who was the expert on switching. And not only that, but in his inimitable organizational ability, he even found a fantastic student, Charlie Bamber, another Canadian, and he steered him into our project, and Charlie became a very important person in the experiment that we'll discuss. Now, what about the experiment? Why am I talking about something that was done 20 years ago? I feel embarrassed hearing all these new things that people are doing, but I guess that's the way life goes. And after all, this is a retrospective meeting to celebrate Gerard's accomplishments over the years, so we can go back. And the experiment wouldn't have been done without the T-tube that Gerard had just invented at that point. Now, there's also another reason I'm a little bit talking about this, is because I want to demystify this idea about the vacuum breakdown. It's been a buzzword floating around, but as you will see, it was done, and it can be easily done without too much trouble. And also, let me not give away the punchline, but we didn't find anything different when we got to the Schwinger field, to the very strong field. Now, let me go a little bit here ahead. The experiment was done by a collaboration between Rochester, because Gerard had left already for Michigan at that time, otherwise he would have been with us. Princeton and SLAC, it was done at SLAC, and the University of Tennessee. And this is the papers, so you see it's really ancient history, as you can see. It's going on. So now, what do we have here? Schwinger, many years ago, it's more than 50 years, pointed out that if you have a strong electric field, then electron-positron pairs can pop out of the vacuum. And even though Schwinger has this beautiful paper of how this is done, it is easy to understand on elementary basis, because I call it the Cinderella effect, because Cinderella had only a certain time to be beautiful, and so in a short time, these electrons, the virtual electrons, can appear and disappear out of the vacuum, And what is that time? That time is, of course, the Compton wavelength divided by c, and it's of the order of 10 to the minus 24 seconds. Now, if during that time beautiful prince appears and takes Cinderella along, then maybe she can become a princess too. So how do you do that? If you have an electric field, the virtual pair, the electron will go one way, the positron will go the other way, so they'll conserve momentum, but as they travel, they both will gain energy. And if they gain enough energy to exceed their rest mass, that is, this is the energy that's pointed there. Let's see if I can find, speaking of pointers, if they can gain enough energy in this short time to be equal to the rest mass of the electron, then they will become real electron-positron pairs. And what is the field that you need to do that? I mean, this is all freshman physics at this point. Oops. I better go back quickly. This field is 10 to the 16th volts per centimeter. And this has been a little bit of a holy grail, excuse me for using that word, as a laser benchmark. You know, if you want to get to that field. But there is one important constraint. If you try to do it with lasers, you can't make a pair unless the invariant of E field minus B field squared is larger than 0, because for the electron-positron pair, this invariant is larger than 0 since they're real particles. So you see that with a plane wave, this is 0, so you would not break down the vacuum, the plane wave. That's now well understood and believed generally. You can think of various variations, and in fact, I'll come back of how you do it. Of course, everybody knows what you do is you try to make a standing wave. But then you are in a different type of physics than the Schwinger physics, I mean, because we'll come back to it. Now, what did we use? What we used is we took the T-cube laser and shipped it not to Michigan but to SLAC, so we moved it to SLAC, and what we had is a typical terawatt of that time. That is, this is late 80s, okay? It's 10 to the 12 watts, and we could focus it down as well as we could, and you get an electric field at the focus of 10 to the 10th volts per centimeter, while we were looking for, this thing is, it's the one that's rubbed out, this one here. No, I don't want to advance, I wanted the pointer. That's the one that kills me all the time. So we are 6 orders of magnitude almost away from the critical field. But now, when you can think, of special relativity, if you view this laser from a frame of reference that's moving with high velocity, say a velocity within 10 to the 1 part in 10 to the 10th of the speed of light, then the electric field seen by that laser is amplified by the gamma factor, which is, for this velocity, is 10 to the 5. So you can get now, the electron sees a field which is 10 to the 15th volts per centimeter. And what we have gained a factor of 10 to the 10th in laser power by scattering the laser from the high moving electrons. And so if we put our numbers in, what the electrons see, they see an equivalent laser field corresponding to a 10 to the 22 watt laser. That is to a zettawatt laser, 10 zettawatts if I have my arithmetic correct. So where do we find such a frame of reference? Well, if the electron as at slug had an energy of 47 GeV, then the gamma factor is very close to 10 to the 5. And out of completeness, the peak values that we reached at that experiment, the peak values we reached was an eta, or the multi-photon parameter, or the Keldysh parameter, as we just heard in a previous talk, was 0.3. But the Schwinger exponent, this upsilon parameter, also which goes by different names in different countries, maybe now that there is an international laser union, they will decide also on having international symbols rather than reading Xi on one and Chi on the other. So we reached fairly close to the critical field. We had a value of 0.16 for that thing. Now, how did the experiment work? Well, if I can get that crazy thing here to work. So we have this electron beam, which is 47 GeV. The electron beam comes in. Here's the laser focus, and it backscatters. It backscatters from one of these 2 EV photons, and the backscattered photon now has an energy of about 28 GeV. So we have a 28 GeV photon, which then interacts with the rest of the laser within the same focus. It never gets out. Originally, the original plan of the experiment was that we would take these photons, take them down to another intersection region, and have the laser again there and collide with them. But nature was good, and this happened right away. And then this is how the pair is being produced. If you want to think in terms of Feynman graphs, it depends which way you like to think, this is what is happening, and it's a two-step process, just as indicated here. One vertex here, one vertex there. So you first make the backscattered, this is standard Compton, and then the backscattered photon now has to interact with several of the laser photons. Why several of the laser photons? Because there isn't enough energy. You see, the laser photons are 2 EV, and the backscattered photon is 28, and if you do the arithmetic, it's not enough to make a pair. There isn't enough energy. So you need at least 4 photons from the laser beam. You need at least 4 photons plus 1, 5, plus the one you used before, total, to make a pair, because you want the energy in the center of mass to be over an MeV. So now, having said that, how was it implemented in practice? Here is the 47 GeV electron beam coming down. So the electron beam is, forget it, is coming down, and there is a set of magnets, permanent magnets in fact, which now deflect charged particles. And if they are positrons, the positrons will go up to an upper calorimeter, the electrons go down into a lower calorimeter, and the photons go straight forward. The straightforward photons can be measured in a pair spectrometer by converting them, and we did that too, but of course, what I'm talking about now is the production of the pairs. How do we, what other things do we have to do? After all, the electrons and the laser must be synchronized. That was our concern when we started the experiment, whether it would work or not. And it's reasonably easy to do because you take the a subharmonic from the frequency of the LINAC, LINAC frequency, and you drive the mode locker in the laser. So the pulses are now synchronized, and this is what you see now. So this is a coincidence curve. This is picoseconds. Of course, today we were hearing about attoseconds. I mean, picosecond was barely spoken. But on the other hand, here, the electrons start 2 miles away from the detector and from the laser. So it's a long way down. And it was remarkable. We were, holding our fingers crossed that we would see collisions. And so one can make these coincidences happen. Now, there's something more interesting, and I guess this I have to give lots of credit to Charlie Bamba, because he kept saying, well, look, how do we know that the electrons go through the focus of the laser? Because after all, this high intensity and the high field we have been talking about happens only at the focus. And here you can see one of these funny topologies that happen sometimes in physics. Here is the electron beam, and here is the laser beam, and this is roughly the relatively, this is the electron beam in blue, and here's the laser beam coming down at a 17-degree angle. And if they're not aligned, you can have still lots of comptons and even not so many nonlinear, linear comptons, because the electrons cross the laser even if they're off in position. You simply have to change the time. I guess they interact with the laser later. It's only when they're here. So how can you do it? You can raster. You can move the electron beam up and down. Oh, well, this is right and left. It's in the horizontal plane, and you can delay it. And this is what you see here. That if you're looking at linear scattering, just Compton scattering, then you can find the scattering any place as long as you offset the beam so as to meet the 17-degree angle and delay it accordingly. On the other hand, if you look at nonlinear effects, and we had, of course, lots of two-photon scatters, which you can use for calibration. You see that's only at one place at the center when they overlap here that you see nonlinear effects, because this is the only time that you go through the high field. Now, just a little bit of instrumentation talk. How do we know that we see positrons and electrons? And this is because we have this calorimeter, if you want to call it, where we can measure both the the momentum and the energy. And since these things are highly relativistic, obviously energy and momentum must be equal. So you see a peak at 1 here. Well, how do we get this peak? We didn't make all those electrons with the laser. You just put a wire there where the laser was, and then of course the electrons produce zillions of pairs, and sometimes they produce even 2 and 3, and you can map the thing out. Now, what are the results? Well, you have, of course, two options. You turn the laser on or you turn the laser off. That's your background. And because how can you know that the positrons that you see are coming from the laser? Well, you just take the difference between these two, and it is convincing. And if you plot the spectrum of what you see, you see just a plot like this, which is close to what it should be. There are not too many events here. There are about 100, but the momentum spectrum should peak at the half of the energy of the high energy photon, which was, of course, 28 GeV, so around 14. This is what we expect. Now, let's plot the results, and what I'm going to show is the number of positrons. That is, if you see positrons, you made a pair, number of pairs as a function of the Keldysh parameter. And this is the eta at the laser focus. And obviously, it being a multi-photon effect, in this perturbative calculation, it goes as eta to the 2n. And in fact, this is the plot. This is eta to the 10th. Now, where is n5? As I said before, you need at least 4 photons to make a pair after you made the high energy gamma. So you need 5 photons for the process to proceed. And therefore, you expect it in this picture. You expect this picture to go as eta to the 10th power, which is what you see here. Now, we can also do a direct calculation. We did a Monte Carlo, and this gives you the number of positrons per Compton scatter, per back-scattered photon. And of course, since it's a 5-photon process, it is fairly rare as compared to the one photon process of the Compton scatters. And here, this is the calculation. This is a theoretical calculation in the multi-photon, that is the perturbative domain. This is what you would get if you had tridents, because that was an argument. Do you see really this 2-photon process, or do you see direct production of the pair from the first vertex? So there is exact calculation with the multi-photon formalism, but also I had a note here. It's a little silly, of course, but it's a log-log scale, so it moves very fast as eta moves from 0.2 to 0.3. Below that eta, of course, all you see is background. You don't make enough pairs. But then we can also fit the data or calculate the data according to the Schwinger argument, the breakdown of the vacuum. And here is the same data, but now plotted as a function of this upsilon parameter, or as we said, xi, whatever people use, the Schwinger parameter. Of course, you plot it as 1 over this because you expect an exponential dependence in the inverse of that parameter. And the data also is now at 2 different energies, and you see the greens are the lower energy, the yellow ones are higher energy. They all fit together. But then you have to do some theoretical shenanigans. Why? Because Schwinger's exponent, which was pi over something, Schwinger's exponent is for a static electric field. But there are papers, now the name escapes me, the French people have calculated what happens in an oscillatory field rather than a DC field. And if you do the corrections for the oscillatory field, you predict a slope of 206 and you see 2. So just to take 1 minute to recap what I was trying to say, it's interesting that at this intensity, that is at upsilon of about 0.6 or whatever our value was, and the one is in between the perturbative and the non-perturbative domain exactly. So that was, I don't know, maybe a freebie of the experiment, not that we planned it this way. I mean, if one went to higher energies, one would be completely in the Schwinger domain. One went down, well, then one would need more photons, one had less energy, and would have only a perturbative calculation. And I would like to conclude with just a brief discussion of this experiment. As we said, if you try to break down the vacuum with a laser field, you need to make the invariant larger than 0. How can you do this? You can do it by a standing wave, okay? So you bring the two beams together and you make a standing wave, and you go at the places where you have a pure electric field. But if you have a standing wave, all you are doing really is you are doing photon-photon scattering, because the two beams are colliding one with the other. So it's almost, it's not the Schwinger process itself, because you are doing photon-photon scattering and you're not breaking the vacuum down with a static field. And here are the standard diagrams for photon-photon scattering. Well, of course, the elastic one is the Delbrück scattering, which goes like this, and the inelastic is the one that we observed, even though in the SLAC experiment there were also lots of elastic scatterings, but we never measured them. But what we measured is photon-photon comes in, and you get a pair out, except, of course, that here there were 4 photons. Again, it's a little bit simplified. Now, the cross-section for this was calculated by Bright and Wheeler, I don't know, in 1937 or sometime like this. And the cross-section goes as the product of the energies of the 2 photons, and it is of the order of 10, I mean, for optical photon frequency, 10 to the minus 30 microbarns, okay? So this is why it has not been seen as yet, in spite of concentrated efforts, or I mean, very serious efforts. Well, why were we able to see it, and without being even super smart? Because simply one of the photons was 28 GeV. So it's 28 GeV as compared to 2 or 3 GeV. You have a factor of 10, you raise to the cubic power, so 30 orders of magnitude more, and we get a cross-section of almost a microbarn, which is observable. Well, I think I'm finished. I have a slide here which simply shows how the cross-section looks, which many of you are familiar with, and anyhow, we showed it in the previous slide. It peaks around when the center of mass energy of the 2 photons is equal to the rest mass of an electron, and then, of course, then it falls off. So it has a long way to go up. Well, as I said, I feel embarrassed for giving you old history of 20 years ago, but it reminded me of the good days we had in Rochester with Gerard and with his group, and some of his group is still around here, and it was nice meeting them at this time. Happy birthday, Gerard. Yeah, sure. Well, good to see you.
Adrian.
next is Jason Chen from the National Taiwan University. I think he's come the greatest distance. Is there anyone who's come from further than Taiwan? Okay, so Jason is going to tell us about laser cosmology.
Can you plug this computer on? I'll get them wired. Did you need sound?
No, I don't.
Okay.
Is there a way to make it tighter?
That should be good. There's your device. I don't know how to make that sound.
Yeah, that's the one thing we were doing this morning. It's
Keyboard?
it's control right.
That's to the back side. We're going to go to this,
Which?
to this one, but I don't know the rules.
Oh, to the house. No, no, you're using Mac, right?
It is a Mac, but it's not the Mac down there. It's this one up here.
Yeah, but that's. Oh, I see what you're saying. Oh, Chris, I don't know. That's the one combination we have now.
Check and see if,
Chris just now used his on.
okay.
Yeah, there it is. There it is. Okay.
Okay. Oh, that's not yours.
That's the house.
We'd like the external Mac. This flash, that's a good thing. Is that good? There, huh? There's a signal. Now give me the signal. Okay, this is your other screen. Do we need to put you into displays? And shall we mirror displays? We'll try it this way in any case.
Yes, it's right.
Okay, and then we'll try play. So it may be that your screen is not exactly right, but the laser pointer is the line and the forward is the black key.
This is a wonderful occasion, and it's been pretty late afternoon, and I am sure you're all waiting for our birthday boy Gerard's talk after me. So, let me try to be as swift as possible. This is tremendous honor and pleasure to be here at this very joyous occasion. I remember my first meeting with Gerard is exactly here in Ann Arbor about 20 years ago, around when I was invited by him to the Center for Ultrafast Optical Sciences. So it's a tremendous pleasure to be back here again after, actually, in between time, I don't remember I've been back here. So this is a wonderful occasion. We've heard a lot about the genius inventions of Gerard's during this whole day. I'm in a very modest way trying to pitch in from another angle from cosmology. So without further ado, I like to, I think most of you have all your ears full, but this is really a tremendous exciting time for cosmology, with breaking news pouring in almost by the day. And so for now, after 30 years of effort, we have developed a so-called standard model of cosmology. We now more or less believe that universe is started with a Big Bang, and within an attosecond, 10 to the minus 36 seconds, our universe expanded by of the order of 10 to the